Our speaker is Sucharit Sarkar. He was born in Calcutta, India, and then studied in India and did his PhD at Princeton University under supervision of Zoltan Chabot. Sucharit is currently based at the University of California in LA. He's co-author and the co-presenter of today's talk, who is not here today, is Robert Lipshitz, who got his PhD from Stanford University in 2006 under supervision of Jakob Jashberg. And, well, he is currently based at the University of Oregon. So, please welcome Sucharit. And the talk title is Stable Homotopy, Refinements, and Khovanov Homology.
Thanks for the introduction, and thanks for inviting me to the ICM. I've really enjoyed my stay so far, and everything has been great. So as you mentioned, this was supposed to be a joint talk with my longtime collaborator and friend, Robert Lipshitz. But unfortunately, he couldn't make it to Brazil, so I'll have to do this alone. Also, he designed the slides. And also, let me start by thanking our collaborator, Tyler Lawson, who is a collaborator on a lot of these projects. And really, the perspective that we learned is we learned from him. So let me start with a big thanks to both Robert and Tyler. And needless to say, whatever I'm about to tell you, even if I don't state so explicitly, is automatically going to be joined with Robert and Tyler. OK. So the talk is in two parts. So in the first part, I'm going to tell you about the general problem that we are going to study. Namely, we start with a chain complex, which may be coming from Morse theory or float theory or categorifications, some sort of a natural setting. And then we ask, or rather restate a question by Cohen, Jones, and Siegel, is that can we construct a CW complex whose cellular chain complex is the given chain complex? Okay? And then we'll see that, in general, there is no universal way of doing this. There is no universal solution to this problem. And that follows from a theorem of Carlson. Okay? So we call this a spatial refinement problem. You are given a chain complex. You want to construct a CW complex. So spatial refinement problem, and there is no universal solution to this. Nevertheless, we'll see that when we can solve this spatial refinement problem, it will have some applications. And then I'll list some general strategies of how to solve this spatial refinement problem, since by Carlson, there is no universal strategy. And then I'll describe one of these special strategies, which is a strategy of flow categories, in a bit more detail. OK, so let's start with one of the most fundamental examples of a chain complex, which is the Morse chain complex. So we start with a smooth manifold, assume compact for the moment. Let's take this red sphere, okay, shaped like a heart, and a smooth function, which is a Morse function. So namely, in this case, let's take the projection to the vertical axis. Okay? And then there are critical points. And the critical points, the Hessian is non-singular. So here there are 4 critical points, A, B, C, and D. And every critical point has an index, which is the dimension of its negative eigenspace. Okay? And then if you have this, you can immediately calculate the Euler characteristic of the manifold, which you just take the alternating sum of the number of critical points in different gradings. Okay? So in this case, the Euler characteristic just happens to be 2. Okay? So that's great. But numbers don't form a category. So there are no morphisms between numbers. So if you have a map between manifolds, the Euler characteristics are not going to give you any information. So what you want to do is you want to categorify the whole situation. So that means you want to take some category whose decategorification, or the Grothendieck group, or K0, is numbers. Okay? And the right category in this case happens to be the category of finitely and freely generated chain complexes. And then what you want to do, you want to lift this Euler characteristic to an invariant in that category. And in this case, it does work. So and that's called the Morse chain complex. So the Morse chain complex, the nth chain group is generated by all the critical points of index n. And the differential of a critical point of index np, its coefficient at q, is given by counting the number of flow lines from p to q. So for this, you have to fix a metric, a generic metric, and you have to count the flows of the gradient of f. And you also have to count it with signs. So you have to orient the negative eigenspace of every critical point. Okay, so some technicalities. But anyways, in this case, there are 4 critical points. So the chain group is generated by these 4 generators, A, B, C, and D. There is exactly one flow line from C to B, so the differential of C is B. There is exactly one flow line from D to B, so the differential of D is also B. But there are 2 flow lines from B to A, so the differential of B is 0, because these 2 flow lines come with opposite signs. So that's the chain complex. And if you want, you can take the homology. The homology really has the same amount of information. So in this case, the homology just happens to be Z plus Z, which is indeed the homology of the sphere. Okay? So that was a fundamental example of a chain complex. But let me give some more examples, some more recent ones. So we must start with Floer. So these are the 2 most famous chain complex examples since then. So the Lagrangian Floer complex is a chain complex which is generated by the intersection points between 2 Lagrangians in a symplectic manifold, and the differential counts certain holomorphic strips. And the other one, the instanton Floer complex, it categorifies the Casson invariant of a 3 manifold, and it's generated by the solutions to the Yang-Mills equation. And the Atiyah-Floer conjecture says that it can also be obtained as the Lagrangian Floer homology. There has been some more recent families of chain complexes after this. So namely these 3, they all categorify the Turaev torsion of a 3 manifold. And the Higert-Floer homology is due to Ojwat and Szabo, and it's defined by, it's a special instance of Lagrangian Floer homology. Embedded contact homology is defined by Hutchings and others like Mike Thaddeus, Eugene Lee, Sullivan, and Taubes. And it's obtained by counting some holomorphic curves. And then there is also monopole Floer homology defined by Kronheimer and Rovka and others like Freuscher, Kronheimer, Manelescu, and that's obtained by counting monopoles or solutions to Seiberg-Witten equations. And they all categorify Turaev torsion, and it is now known that these are all the same chain complex. They're all isomorphic, and that's due to theorems by Taubes, Colin Gijini-Honda, and Lee Kutlahan-Taubes. A slightly more interesting example of a chain complex is a relative version, which is, so if you have a knot inside a 3 manifold, then there is a bigraded chain complex. It has an extra grading, and that's due to Ojwat, Szabo, and Rasmussen. And so since it has an extra grading, its decategorification is actually a polynomial, not just a number, and that happens to be the Alexander polynomial of the knot. Okay? And these chain complexes are all Morse type, in the sense that there is some infinite dimensional smooth manifold and some function on that, and your solution, you're kind of doing Morse function on that. Except the main subtlety is that they don't satisfy the Palais-Smell condition for gradient flows, and so there is no guarantee for short time flow. So the analysis is much trickier, and these are much harder to define than Morse homology. But the general idea is the same. On the other hand, there's a different type of chain complexes, and these come from categorifications. So they come from categorifications of quantum Lie groups like UQSL2, and these are very combinatorial in nature, not analytic like these ones. So the main starting example is by Khovanov, which comes from the categorification of UQSL2. And this is also a bigraded chain complex, so its decategorification is also a polynomial, but it's not the Alexander polynomial, it happens to be the Jones polynomial of the knot. And then there are many generalizations. You have a generalization for SLN, you also have a generalization for Humphrey homology, and you also have generalizations for colored Jones polynomial and other Lie algebras, and these are due to like Khovanov-Rozansky, Webster, and many others. Okay? So those were some fundamental examples of chain complexes, and here is one more. This is due to Seidel-Smith. It's Morse-like by definition. So it's an example of Lagrangian Floer homology, but it's conjecturally isomorphic to Khovanov homology. So, and this conjecture has been checked in some cases by Abu Zaid Smith. Okay, so, okay, great. So now, here is a fundamental question that we are asking. This is the main problem, that we have all these chain complexes, and they come up in natural settings, like Morse functions or Floer theory or categorifications. These chain complexes all come with a canonical basis, so which happens to be the critical points in the Morse case, or which happens to be the intersection points of 2 Lagrangians in the Lagrangian Floer case. And here is a question by Cohen-John Siegel, that can you construct a CW complex whose cellular chain complex is this given chain complex? Okay, and by the way, we don't, and the generators should be the cells of the CW complex. And in general, we don't really expect, we expect these spaces to be constructed stably. So we expect a spectrum, not a space. And sometimes we only expect a pro-spectrum. But all those technicalities aside, here is the main spatial refinement problem again. You're given a chain complex with a distinguished basis. Construct a CW complex whose cellular chain complex is the given chain complex with the distinguished basis corresponding to the cells. Okay, how do we do this? So here is that question once again in terms of functors. So you have the category of CW complexes, and then there is a functor which is a reduced cellular chain complex, and that's a functor to the category of chain complexes. And the functorial version of the spatial refinement problem asks, can I construct a section of this functor? And the answer is we cannot. Okay, so this is the theorem of Carlson, which says that there is no functorial way of constructing this section. Non-functorially, you can do this. That's called the Moore space construction, but functorially, you cannot do this. Okay, so there is simply no universal way of constructing a CW complex from a chain complex. Okay, so and the proof is basically he constructs an abelian group with a Z2 cross Z2 action, and he shows that it doesn't come from a space with a Z2 cross Z2 action, and it kind of follows from there. Okay, now this is actually good news because this means that we have work to do. And it also means that any time we can solve the spatial refinement problem, it will not be automatic. So it will actually contain extra information than the information that's already contained in the chain complexes. Okay? So this brings us to this slide, that every time you can construct spatial refinements, you get applications. Like, for example, as it's well known, spaces, even stably, have more information than chain complexes. So stably, a space won't have cup products, but it will have cohomology operations, like Steenrod squares. So that will be a lot of extra information. And you can also have extra cohomology theories, like stable homotopy groups or K theory, and that's all extra information for spaces, which is simply not available at chain complexes. And this information gap is even more stark for maps. So maps between spaces generally have much more information than maps between their homology groups. So for example, if M is bigger than N, then maps from SM to SN constitutes an entire field of study. These are called homotopy groups of spheres. But at the level of homology, there is simply no information. And there's also an interesting feature that comes up when there's a group action involved. So if there's a group acting on a space, then you can talk about fixed points and quotients, and you have different homology theories like the Borel equivariant homology. But if you have a group acting on a chain complex, there is simply no good notion of fixed points. So there is no good localization theorem. So at the level of spaces, you have these nice localization theorems, and these are called Smith theory, but there is simply no such thing at the level of chain complexes. So having a space is much better than just having a chain complex. Okay, so now that we understand that we want to construct spatial refinements, and we know how good it is, like what are the main applications, but we also realize by Carlson that there is no universal solution for this. So what do we do? So let me list some general strategies that we can use to solve the spatial refinement problem. So one of the first strategies is due to Cohen, Jones, and Siegel, so who basically package the data of higher dimensional moduli spaces into something they call a framed flow category. And then they use basically the Pointryagin-Tom construction to convert a framed flow category into a space. Okay? So this is actually the strategy that we used to spatially refine Khovanov homology originally. So this was the strategy that we used. There is some other strategy using Conley indices. This has been used by Manolescu and earlier Kronheimer-Manolescu. So these are supposed to be pictures of Conley indices. You can also use different finite dimensional approximations used by Krag for spatially refining the Viterbo transfer. And here is another interesting strategy. To spatially refine, you can also use functors to some auxiliary categories, like the Burnside category or the category of framed cobordisms. And this strategy was used by Hugh Krish and also us to give a different spatial refinement of Khovanov homology. So these are some general strategies. Now let me tell you a little bit more about one of these general strategies, namely the strategy of the Cohen-Jones-Siegel strategy of framed flow categories. Okay, so what's a framed flow category? A framed flow category is basically a way of encoding the data of higher dimensional moduli spaces into a topologically enriched category. So let me do this with an example. So let's continue with the example from the Morse function. So that was our Morse function. It had 4 critical points, and these were the flow lines. So the framed flow category we'll have 4 objects, one for each critical point. So these are the objects. And these objects will have gradings. And the gradings will be the indices of the 4 critical points. So the objects will have gradings 0, 1, 2, and 2. Okay, so those are the objects, and those are their gradings. Now, what are the morphism sets? Well, the morphisms are going to be flow lines. So there is exactly one flow line from C to B, that's that alpha there. So the morphism set from C to B will be one element, that's alpha. Similarly, there is exactly one flow line from D to B. So the morphism set from D to B will be this one element set beta. And there are 2 morphisms from B to A. So the morphism set from B to A will be 2 elements, gamma and delta. Okay, so far so good. But then it gets interesting. What is the morphism set from C to A? So what is the space of flow lines from C to A? Well, you have broken flow lines. So you can flow from C to B by alpha, and then from B to A by gamma. And you also have a different broken flow line. You can flow by alpha and then by delta. So you have 2 broken flow lines. But you actually have an entire one-parameter family of flow lines from C to A. So for example, the leftmost edge of that heart, that's an entire one-parameter family of flow lines. So the moduli space of flows from C to A is actually an entire interval whose 2 endpoints are the 2 broken flow lines. So similarly, the moduli space of flows from D to A is also an entire interval, the red interval, and its 2 endpoints are the 2 broken flow lines. So that's basically a flow category. So it's a category whose moduli space, whose morphism sets are flows, and it also has to be framed. So this flow category, the moduli spaces are all smooth manifolds. So you also have to frame their stable normal bundles, and these framings have to be coherent in some sense. So there is some framing data. But the moment you have this, you can immediately convert that into a CW complex by this Pointryagin-Thom construction. So what you do is you have a cell for each object, and its dimension is going to be the grading of that object plus some large constant. Okay, so these are going to be my cells. And this large constant, well, let's do this example. So let's take the large constant to be 1. Okay, and you need a base point. So you have a base point. Great. So now I need a cell for A. So A had grading 0, so I need one cell. So that's the one cell, this purple one cell. And I have to attach its boundary to the base point. So that's my one skeleton. Now I need a 2 cell for B. So that's my 2 cell for B. Now on its boundary, there are these 2 purple intervals. And these correspond to the 2 flow lines from B to A. So the moduli space from B to A was 2 elements, gamma and delta. So these 2 purple intervals on the boundary of B, they correspond to the 2 intervals, two morphism elements from B to A. And you glue them to the 1 cell for A. And you glue the rest of the boundary of B to the base point. Okay, so that's your 2 skeleton. Now for C, I need a 3 cell. So that's my 3 cell. So on the top, there's this light gray semicircle. That corresponds to the flow line alpha from C to B. So the moduli space from C to B is a single element alpha. So that corresponds to the top semicircle. And that gets glued to the cell for B. And then there is this purple strip that corresponds to the one-dimensional moduli space of flows from C to A. And so that entire purple strip gets glued to the cell for A. Okay? So and the rest of the boundary gets glued to the base point. So that's how you attach the cell for C. Similarly, there is a 3 cell for D. It also gets attached like that, and that's your CW complex. So if you have a frame flow category, you can construct a CW complex like that. And in this case, the CW complex just happens to be a single suspension of S2, a one-point compactification of S2, that's starting manifold. Okay, so that's your that's the construction. So that's one strategy of like constructing a framed flow category. Great. So now let's move to the second part of the talk. The second part, so the first part was like we are giving you general strategies on how to construct spatial refinements. But in the second part of the talk, I'm going to give you one specific example. Okay? So we'll start with a specific chain complex. Our success story is with the Khovanov chain complex. So we'll start with Khovanov chain complex, and we'll spatially refine that. Okay? So we'll put these general strategies into action. Okay? And so even if you haven't followed the general strategies so far, you should still be able to follow this specific construction. Okay? So So what we do is like, I'll recall the definition of Jones polynomial. The Khovanov homology is actually a categorification of the Jones polynomial. So then I'll tell you what the Khovanov homology is. I'll state some well-known classical applications of Khovanov homology. And then I'll give you the general structure of the Khovanov homotopy type. Like how do we construct the Khovanov homotopy type? And then I'll give you how to construct it. So we'll use the extra functors to Burnside category to do that. So I'll give you the general idea of how to construct the Khovanov homotopy type, and then I'll tell you about some extensions that have appeared since, and some applications of Khovanov homotopy type, and I'll end with some open questions, okay? So let's start with the Jones polynomial, okay? So the Jones polynomial, how is it defined? So you start with a knot projection. So let's take this two crossing diagram of the unknot, and you need to number the crossings. Okay, so let's number the crossings. I know it's not the most interesting knot, but let's stick with this for simplicity. Okay, so now each crossing can locally be resolved in two ways: the 0 resolution or the 1 resolution. Okay, so there are n crossings, so they can be resolved in 2 to the n ways, and they form a cube. Okay, so for example, at 0, 0, you are resolving both the crossings by the 0 resolution, but at 1, 0, you are resolving the first crossing by the 1 resolution and the second crossing by the 0 resolution, and so on. So that's called the Kaufman cube of resolutions. Okay, you took at all possible ways of resolving this knot diagram. Okay, and then you just take a state sum over this cube. That means you sum over vertices of the cube, and you sum minus q raised to the height of the vertex, and then q plus q inverse raised to the number of circles in that resolution. So for example, at 1, 1, the height is 2, so you do minus q squared, and there are 2 circles, so you do q plus q inverse squared. Okay, so that's the contribution from 1, 1. And similarly, you have these contributions from the other vertices, and you just add them up. And if you just add them up, you get the Jones polynomial up to some monomial, this plus minus q to the n. Okay, up to some monomial, which I'm going to ignore, you just basically get the Jones polynomial. And in this case, it happens to be q plus q inverse for the unknot. So that's it. That's the Jones polynomial, this extremely simple, yet extremely mysterious invariant of knots. Okay? Now what Khovanov does is he categorifies the entire story. So that means, so he starts with the Frobenius algebra. So Frobenius algebra, that algebra right there. So Frobenius algebra means that in addition to a multiplication, you also have a co-multiplication, and which is coherent with respect to multiplication. And Frobenius algebras can be thought of as a 1 plus 1 dimensional TQFT. So what does that mean? It means that to a circle, so to a circle, I assign this algebra, V. And now, to a disjoint union of circles, I assign the tensor product of this algebra. And now, for cobordisms, I have to assign maps. So all the cobordisms come from the simple cobordisms. I can take 2 circles, and I can merge them to form a single circle. So for that, so that's a merge. And for that, I need a map from V tensor V to V. And that's just the multiplication map. But I can also take the dual, which is I can take a single circle, and I can split it to become 2 circles. So for this, I need a map from V to V tensor V. And that's the co-multiplication map, which for this algebra sends 1 to 1 tensor x plus x tensor 1 and sends x to x tensor x. Okay, so that's your Khovanov-Frobenius algebra. That's a 1 plus 1 dimensional TQFT. So what he does is he takes this Kaufman cube of resolutions from the last slide, and he applies this 1 plus 1 dimensional TQFT to that. So what does that mean? So at the 0, 0 vertex, I had 2 circles, so I should get V tensor V. At the 1, 0 vertex, I had only 1 circle, so I should get V. Okay, similarly at the 0, 1 vertex, I had 3 circles, so I should get V tensor V, and so on. So I get abelian groups at the vertices of the cube. And now these groups actually have gradings. So if you take the graded dimensions of these groups, you will get the polynomials in Q from the last slide. And then that's enough to recover the Jones polynomial. But last time, what we did was we had those polynomials in Q, and then we added and subtracted them. Now, subtraction doesn't really make sense for abelian groups. So what we do instead is we make this into a chain complex. So the idea is that along the edges of the cube, you actually have cobordisms. So along every edge of the cube, you either merge 2 circles to make a single circle, or you split a single circle to make 2 circles. Okay? And so you can apply the Khovanov TQFT and you get maps. So for example, along the lower horizontal edge, you are merging two circles to become one circle. So you apply the multiplication map from V tensor V to V. But on the rightmost edge, you are splitting a single circle to two circles. So you apply the co-multiplication map from V to V tensor V. So you get a commutative cube of abelian groups. And once you have a commutative cube of abelian groups, you can take the iterated mapping cones. Okay, you take mapping cones in the vertical direction, then you take mapping cones in the horizontal direction, and so on. So that's kind of like flattening the cube along the height. Okay, if you flatten the cube along the height, you can get a chain complex out of it, which happens to be this. And that's a Khovanov chain complex. And then if you want, you can take its homology, and that's the Khovanov homology. So in this case, for the unknot, it happens to be z squared, which does categorify q plus q inverse. Okay, so that is the Khovanov homology. It's defined using this Khovanov cube. Okay, so what is this good for? Okay, this extra categorification, this extra structure, what are some famous applications of Khovanov homology? So maybe the most famous application of Khovanov homology is due to Jake Rasmussen. So he proved that for positive knots, the 4-ball genus equals the 3-ball genus. So the 3-ball genus of a knot is a Seifert genus. That's the smallest genus of a Seifert surface for the knot. But the 4-ball genus is the smallest genus of a surface inside the 4-ball which bounds that knot, okay, oriented. And so in general, the 4-ball genus is smaller than the 3-ball genus, but Rasmussen showed that for positive knots, they're actually equal. And you prove this using Khovanov homology. And in fact, they're equal to this very simple formula, n minus k plus 1 by 2, where n is the number of crossings and k is the number of circles in an oriented resolution of a positive knot diagram, okay? So in particular, the PQ torus knot is a positive knot. So for PQ torus knots, the 4-ball genus and the 3-ball genus are equal, and they also happen to be same as their unknotting number. The unknotting number is the smallest number of crossing changes you need to do to unknot a given knot. And for torus knots, they all happen to be p minus 1 times q minus 1 by 2. So this was conjectured by Milner in his book, Singularities of Complex Hypersurfaces, and was earlier proved by Kronheimer and Rofka using instant-on gauge theory. So for example, the knot along the border, that's a 568 torus knot. And so this tells you that you need 134 crossing changes to unknot that, okay? So here is another famous example. So this one is due to Kronheimer and Rofka. So we saw from the previous slide that the Khovanov homology of the unknot was two-dimensional. And Kronheimer and Rofka say that the converse is also true, that if Khovanov homology of a knot is two-dimensional, then it must be the unknot. So this tells you that Khovanov homology detects the unknot. And by the way, the corresponding question for Jones polynomial is wide open. So we don't know if Jones polynomial detects the unknot. That's a big open conjecture. It has been checked for all knots up to 22 crossings. That's around 1 trillion knots. But okay, so it seems pretty solid. Okay, so that's all about Khovanov homology. So what we want to do is we want to get a stable homotopy refinement of Khovanov homology. So for a link diagram, you get Khovanov homology. And what we want to do is we want to construct a CW complex whose chain complex is the Khovanov chain complex. Okay, actually we dualize when we go to spaces. So actually the co-chain complex is the Khovanov complex. And now if you have a Reidemeister move from a link diagram to another link diagram, then Khovanov constructs isomorphisms of Khovanov homology, and they lift to stable homotopy equivalences. And more generally, if you have a knot cobordism from a link to another link, then Khovanov constructs maps between Khovanov homology, and they lift to maps on Khovanov homotopy types. And again, since we dualize, the maps go the other way. Okay, and this immediately has many corollaries, because once you have a homotopy type, a stable homotopy type, you get these Steenrod operations, the Steenrod squares, and these tell you that all the Steenrod squares are natural with respect to Khovanov cobordism maps. And then we also have explicit formulas for the Steenrod squares. And you can use this, you can compute the Steenrod squares for knots, and you can find examples, like Cottonseed has found examples of knots which have isomorphic Khovanov homology but different Steenrod squares. So therefore, they have different Khovanov homotopy types. So this tells you that Khovanov homotopy type is a strictly stronger invariant than Khovanov homology. So it's a much stronger invariant. And in fact, using this and some formal properties, you can find examples of knots where any given Steenrod square is non-zero, any Steenrod power, okay? So okay, great. So that's some structure of the Khovanov homotopy type. But how do we construct it? So we had originally constructed the Khovanov homotopy type using the framed flow categories from the first part of the talk. But now let me give you a different construction due to Hoo-Krish, and they use the Burnside category. So that'll be a different strategy. Okay, so what's the Burnside category? So this is a strategy used by Hoo-Krish. The Burnside category is a weak 2 category. It's a very simple weak 2 category. The objects are finite sets. The morphisms from X to Y, those are finite correspondences. So with a source map and a target map, you compose by fiber product. And these are 2 categories, so there are also 2 morphisms. So 2 morphisms are bijections between correspondences which respect the source and target map. Okay, so that's your weak 2 category, the Burnside category. And this simple 2 category actually has a functor to the category of spectra, or topological spaces for simplicity. So what it does is on objects, it sends a set X to a wedge sum of the sphere spectra over the elements of X. Okay? And now on morphisms, it's much trickier. So to define this functor on morphisms, you have to factor this through the category of all permutative categories, and then the functor from the category of all permutative categories to the category of spectra comes from this Elmendorf-Mandel infinite loop space machine. So that's fairly technical, but we actually give a very fairly explicit construction of this functor using the Pointryagin-Tom construction. So you can also describe this functor very explicitly. So it's not that mysterious. Okay? But so there is a functor from Burnside category to the category of topological spaces. That's the thing we should remember from this. Okay? So then how was the Khovanov homology defined? So the way Khovanov homology defined was we had this commutative cube of abelian groups, like C00, C10, C01, and C11, and maps between them. And then Khovanov totalized it. So that means he took iterated mapping cones. So we took mapping cones in the vertical direction. Those gave me chain complex sets. And then I had an induced map on the horizontal direction. And then I took mapping cone of that. And that was the final Khovanov chain complex. Okay? So now, to get a CW complex, refining that, it's enough to spatially refine the original cube. So that means it's enough if I can get spaces, Z00, Z10, Z01, and Z11, and maps between them, so that if I take the cochain complex, I get the original cube. Okay, remember, we are dualizing, so the maps are going in the other direction. But if I can spatially refine the cube, then I can still take iterated mapping cones, just as before. So I can still take mapping cones in the vertical direction, then mapping cones in the horizontal direction, and that will give me a space, and whose cochain complex will be the Khovanov cochain complex. So the main thing is that if I want to construct a Khovanov homotopy type, it's enough to just spatially refine the Khovanov cube. And by the way, instead of taking iterated mapping cones, you can do it all at once by homotopy colimits. And you don't even need all these cubes to strictly commute. It's enough if they are homotopy coherent. But anyways, all that aside, how do we construct a commutative cube of spaces? And the idea is you use the Burnside category. So to construct, since there is a functor from the Burnside category to the category of topological spaces, to construct a cube of topological spaces, it's enough to construct a commutative cube in the Burnside category. So that means it's enough if I can construct sets of the objects in Burnside categories, X00, X10, X01, and X11, and maps between sets, so which are correspondences. So and correspondences, those correspondences along edges, and this has to commute. So that means, what does it mean? That means if I compose along one of the directions, that means take the fiber product, versus if I compose in the other direction, the other fiber product, I should get the same thing. So that means there should be a two morphism connecting them, a bijection between those. And these bijections also have to be coherent in a certain sense. Okay? So it's enough to just construct a cube in the Burnside category if you're going to spatially refine Khovanov homology. And how do we construct this Khovanov Burnside functor? Okay, let me just give an outline. So again, we start with a knot diagram. So now let's take a two-crossing diagram of the unlink. Again, not the most interesting knot, but again, let's take this, and let's checkerboard color the complement. Okay, we need to checkerboard color the complement by these orange and white colors. Okay, and then again, you take the cube of resolutions as before. So you have these resolutions on the vertices, and you have these cobordisms along edges, and also along diagonals. And notice that this checkerboard coloring persists on the resolutions, and these cobordisms are all embedded in R2 times the interval, and their complement also gets an induced checkerboard coloring. Okay, so this checkerboard coloring just persists everywhere. Okay, great. So now what is this Khovanov Burnside functor? So on objects, which are a vertex of the cube, on a vertex of the cube, I have a complete resolution. So the set that I associate there is the set of all possible labelings of those circles by 1 or x. Okay, let's do an example. So for example, let's take the 1, 0 vertex. The resolution there is 2 circles. So the set is a set of all possible ways of labeling that circles by 1 and x. So you can label, so there are 4 elements. You can label both circles by 1, or the first one by 1, the second one by x, the first one by x, the second one by 1, or both of them by x. Okay, so that's the set of labelings. That's easy. Now on morphisms, I need correspondences. Okay, so that means if I am given a starting vertex and an ending vertex, and a labeling of the starting circles and a labeling of the ending circles, I have to specify the correspondence from that starting labeling y to the ending labeling z. Okay, and this set is usually empty, except in the following 2 cases. So along an edge or a diagonal, we have these cobordisms, which I have shown. So you have these cobordisms, and so if the cobordism has genus 0, then this, and if the cobordism has genus 0, and this simple condition is satisfied, then this correspondence set is a 1-point element. Okay? So for example, this rightmost edge, let me draw the rightmost edge, that's a split. You have a single circle and the cobordism is a split from a single circle to 2 circles. So that's a genus 0 cobordism. So the starting set is 2 elements. It's 1 and x, because you have 1 circle, you can label that in 2 ways. And the ending set is 4 elements, because you have 2 circles and you can label them with 4 ways. And the correspondence is just points. It's just 1 element correspondence. There is a 1 element correspondence from 1 to 1 tensor 1. There is a 1 element correspondence from x to 1 tensor x. And there is 1 element correspondence from x to x tensor 1. So that's fairly simple. And then the only other case, when the cobordism is non-zero, if the genus is 1. If the genus is 1 and this condition is satisfied, then the correspondence set is 2 elements. And we really have to specify what the 2 elements are. So for example, the diagonal cobordism from the 1, 1 vertex to the 0, 0 vertex, that's a genus 1 cobordism. And then we should have 2 elements, and this is where the checkerboard coloring comes into play. These 2 elements happens to be the 2 generators of a particular cohomology group related to this checkerboard coloring. So in this case, the 2 elements are like are the 2 generators of some cohomology group, which send the purple circle either to +1 or this purple circle either to -1. Okay, so some generators of cohomology groups. And by the way, the Burnside category is a 2 category, so I also have to specify what happens on 2 morphisms, but that's even more technical than this. So let me skip that. So that was, anyways, just an outline of the Khovanov Burnside functor. But the moment you get a Khovanov Burnside functor, you get a commutative cube in the topological spaces, and you get a spatial refinement of Khovanov homology. So the rest just follows. And there have been many further chapters to this story. So for example, so this definition that I just gave you is due to Hukrich-Krish. Our original definition was using the Cohen-Jones-Siegel's framed flow categories. So we proved that these 2 definitions are equivalent. Jones, Loeb, Schutz, and Jones, Orson, Schutz, they carried out many computations of this Khovanov homotopy type by simplifying the underlying framed flow categories. Then Loeb, Orson, Schutz, and independently Willis, they give an extension to colored Khovanov homology. So they have a spatial refinement for colored Khovanov homology. And then Jones, Loeb, Schutz, they also have an extension for SLN homology, but only for a certain class of knots called match diagrams. Okay, so not for all knots. And then with Matt Stoffrigen and Chris Caduto, I give an extension for Ojvat, Rasmussen, Szabo's odd Khovanov homology. And Borojic, Politarchik, and Silvero, and independently Musit, have given extensions for periodic knots. They have Khovanov homotopy types for periodic knots as well. And just like Khovanov homology had many applications, the spatial homotopy refinement of Khovanov homology also has many applications. So for example, Plamonevskaya had constructed an invariant of transverse knots, which is an element in its Khovanov homology. So with Lenny Ng, we lifted that to an element in the Khovanov cohomotopy group. And that's an invariant. So it's an element of the cohomotopy group of the Khovanov homotopy type. And that's an invariant of transverse knots. In a more interesting direction, just like Rasmussen constructed an S invariant, a numerical invariant called S invariant, and he used that to bound the four-ball genus. And he used that to calculate the four-ball genus of torus knots. So using the Khovanov homotopy type, we can refine the Rasmussen S invariant to get a different S invariant using the Steendard squares. And it sometimes improves the lower bound on the four-ball genus by 1. Okay? So for example, for this knot. So this is the knot 942. If you have never seen this knot before, that's a very special knot. So most low-crossing knots are either alternating or more generally quasi-alternating, or positive, or more generally quasi-positive. So in some sense, most low-crossing knots are very special. They're either quasi-alternating or quasi-positive. So 942 is the first knot which is neither quasi-alternating nor quasi-positive. So it's the first knot which is not special in any way. So therefore, it's very special, right? And for this knot, our bound, the refined S invariant, gives a better bound on the four-ball genus than the Rasmussen S invariant. And in fact, more generally, if you connect some 942 with the torus knot, PQ torus knot, its four-ball genus just happens to add up. And it happens to be P minus 1 times Q minus 1 by 2 plus 1. So in general, four-ball genus is very hard to calculate. There are no known algorithms for calculating four-ball genus. So every time you can get information about four-ball genus, that's great news. Okay, so you got some information about four-ball genus. So for example, here is the 5-3 torus knot. And if you connect some of the 5-3 torus knot with 942, that's that, then your four-ball, so then we get information about the four-ball genus of this knot. Okay, so a slightly more interesting application is due to Feller-Lewer-Cobb. So Feller-Lewer-Cobb, so they call a knot to be squeezed if it's a slice of a minimal genus cobordism from a torus knot to another torus knot. And again, most knots happen to be squeezed, and it's very hard to obstruct a knot from being squeezed. And one of the very few obstructions for a knot to be squeezed comes from Khovanov homotopy types. Okay, so these are some applications of Khovanov homotopy types. Okay, so but then we don't know a lot of things. Okay, so let me end with some questions. So all this was a refinement of Khovanov homology, which is a SL2 homology. What about SLN homology? Okay, so so can you construct spatial refinements for SLN homology, or generally home-flipped homology, or other types of Khovanov type homologies? Okay, a slightly intriguing question is this: we have carried out a lot of computations of the Khovanov homotopy type, and we have found a lot of interesting spaces, non-Moore spaces, like RP5 mod RP2, RP4 mod RP1, but we haven't found a single copy of CP2. And now we would have expected a lot of CP2s, but we haven't found a single one. Okay, so this is slightly baffling. So is this just a coincidence, or are they really absent? And if so, I mean, why? I mean, so what's a good reason for the absence of CP2s so far? Okay, what about cobordisms? So Khovanov, associated to a cobordism of knots, Khovanov has this map of Khovanov homologies. Now we do have a map on Khovanov homotopy types, but is this map well defined? The Khovanov homology map is well defined, but is the map on spaces well defined? We don't know. Okay? What about higher naturality? So if I have an isotopy of cobordisms, do I have higher naturality? Or like going further? Okay, so do I have higher naturality? And by the way, for higher naturality, the answer is not even known at the level of Khovanov chain complexes. Okay? And then that's just about Khovanov homology. But of course, we can ask the question about other Floer homology theories. So the Khovanov homology is a very special type of homology theory. But what about Floer homology? What about Lagrangian Floer homology? Can we construct spatial refinements for those? Okay? And maybe we need some extra assumptions, like trivial polarization or no bubbling. So what sort of extra assumptions would we need? And I'm sure there are many more technical issues involved. Okay? So what sort of technical issues are involved, and how do we get rid of those technical issues? And again, we have this space for Khovanov homology, but is there a natural intrinsic definition of this space? Okay? And what about for other Floer homology theories? If you can construct those spaces, can you define those spaces in a more intrinsic geometric way? Okay? And we have many more questions like this in the written version of the talk. Okay, so some technical and some broad spectrum questions. So anyways, so maybe that's where I should stop. So let me conclude by thanking our collaborators on this project, Tyler Lawson and Lenny Ng, And also, on behalf of myself and Robert Lipshitz, would like to thank the many people who taught us a lot of things about this subject, like Mohammad Abu Zaid, Ralph Cohen, Chris Douglas, Ciprian Manolescu. And also, thanks again to the ICM organizing committee for inviting us and for the hospitality. And thank you all for listening.
Wow, thank you, Sucharit, for a very nice talk. Let's ask some more questions.
Thank you for the talk. So you mentioned that there are these two constructions for the Khovanov homotopy type.
That's right.
And you mentioned that you proved that they are
That's right.
equivalent.
Yeah.
But is one easier than the other? Is it easier to extract information about Steenrod squares?
That's right. Actually, that's a good question. Yes, like we wrote down a formula of Steenrod squares using our first construction, using the framed flow categories. And it seems that it's easier to write down formulas for Steenrod squares and everything using the first construction. But I think the second construction, which is due to Hukrish, is easier to describe. So, for example, in this talk, I could even give a brief outline of that. But for the first construction, it would have been impossible to even give a brief outline. So I think the other one is like much more trickier to define. But it's better for actually doing computations, the frame flow categories. So like these constructions, these different computations that have been carried out by Jones, Loeb, Schutz, they all use the first construction. That's easier for carrying out computations.
More questions? I have a naive question. What's special about 942 knot?
Oh, it's like I said, it's like the first knot which is not special. So all the previous knots are kind of special because they are either quasi-alternating or positive. So all the low-crossing knots are special. This is the first one which is not special. The first one which is generic. Okay, so that's, okay, that was, okay, great.
Thank you very much.
Thanks.
Next talk is in half an hour.